Okay, so we were trying to finish off LNAs. So last class we were looking at some other techniques. So the first one we started talking about was current reuse. There are many ways of doing current reuse. This is a very simple basic example. So if you take a single transistor, the transconductance of that is Gm times Vn for a given current. Instead of having a single NMOS common source, you can make it more like an common NMOS PMOS common source amplifier. So the total output current is Gm1 plus Gm2 times Vn. Okay, this is to get more gain for a given current. Okay, so there are multiple ways to do it. This is just a very simple example. You can choose to implement something like this for your LNA. So what you'll have to do is you'll have to do input matching, so obviously the input of each of these is capacitive. So if you want to do 50 ohm matching, you'll have to choose LS for each one of these, and so that the overall input impedance is 50 ohms, and that will still work, right?
And match you will give at the common node, or you will give match for individual?
You will have to give matching for individual, right? So okay, however you match, the overall input impedance needs to be 50 ohms. Okay, the output impedance, let's assume your mixer is capacitive, so that you might, so this is obviously a low impedance node, so you might need to have an inductor or something like that. So you need to find a different way to tune the output. Okay, but this is just an example. There are multiple ways to do it. You can use transformers. There are like many ways to do current reuse. Okay, this is just one way, very simple way. So the next thing is feedback. Okay, so what would you use feedback for? So one thing you can use is, you can use feedback to implement Rn equals 50 ohms. And of course, improve IIP3. Okay, those two things definitely feedback will do. But obvious negatives are noise figure may increase, that's one big thing, and well, yeah, gain will decrease, so that is another thing. But more importantly, okay, so your gain decrease will also lead to impact on noise figure, okay, and increase in power. The other thing is stability. Okay, once you give feedback, you need to worry about stability. Okay, now other general rules of thumb, we talked about some of these last class. So same W by L for cascode, and gate equals VDD. This would be a good place to start. It's a good place to start. So how would you know where to start off with? What to start off with? What minimum size? What is the minimum size? Minimum L is okay. That you're anyway going to do, right? Yeah. So how about W? You need a starting point, right?
Yes, but W also I'm choosing to make normal transistor. If it comes out to be large W, I will not use the same large W there.
Why not? Start with what? So the thing is like this: the larger you start off with, the more headroom you will have for your main transistor, and the better the IIP3 you will get. So you will make the decision to reduce it only after you are sure you meet your IIP3 requirements, right? So when you start off, you don't know what your IIP3 is. You don't know anything about the LNA, except that you know the noise figure, right? You know the power consumption. Those two things you know, but you don't know much more. Okay. And last week we saw you are going to choose W opt and power consumption, so you get some FT. Just try to make sure it's a good rule of thumb, because we saw that at around 10 times F naught for the power constraint optimized width, your noise figure is around 2 dB, 1.9 dB. So this is a good point to start. Try to start off with somewhere around 10 times f naught. If you're starting off with lower, you'll probably have much higher noise figure. Okay. And of course, model noise accurately. Okay. What I mean is gamma and delta. So that is very important. Okay. How about simulation? So you have started off with the hand calculation. So good thing to do for any process is to characterize it so that you know what happens when different things change. So for example, you want to know GM dependence, input impedance dependence and so on, okay, as a function of current, for example, because at the end you are going to change your current, you want to know how it behaves, how your noise behaves, how your GM behaves and so on. So good thing to plot is, most of our hand calculations are for square law devices, right? So, okay, plot Ft, Gm and gamma as a function of I bias and width. What does this give you? For example, if you plot, let's say, Gm versus I bias and width for a given current density, you get your Gm. Okay, and you can also plot the noise of the transistor. Okay, so that might help you in choosing the right size. You can start off, instead of starting off with the W opt, another way to do is to start off with the given current density. Okay, and then move from there. That is another way to do it. Okay.
So VGS minus VD is not a constant. VD sat is not a constant. Typically for analog design, we start with constant VD sat everywhere.
Yes, but in this case, because you're doing, so you would try to do design more for I bias and noise. Okay. Okay, and also remember, so let's call it gain. Usually the optimum point for each one of these will be different. Okay, so what you are trying to find is, you are trying to find, it may be a little bit suboptimal for each one of these, but overall it should meet the specifications. That's what you are trying to reach. Okay. So extrinsic sources of noise. We looked at, MOSFET drain thermal noise, MOSFET gate noise and so on. We looked at the resistor noise. So those are the three different things which usually affect your noise performance. Okay, there are other things. So in this case we are talking about the MOSFET. Okay, so let's look at your CGS, CGD, GM. Okay, what you could have RG, RD, RS. So you could have series resistances due to either design or layout. Okay, you have your bulk, okay, and you could have a resistance from the bulk to the ground. Normally what you assume if it's an NMOS, your bulk is ideal ground, and in this case, okay, you are probably going to design with ideal supplies and ideal grounds, and that's probably okay for a first level class. But if you are doing a real design, you have to worry about all of these things. In your case, you will definitely have to worry about RG. Okay, so let's look at that first. Okay, so what can you do to, what is Rg first of all? It is the resistance of the gate. Okay, so why do you have Rg? So normally gate resistance and drain resistance will usually be pretty small. Okay, in a normal design you will, and in a good layout you will have to worry about Rg and Rb. Those are the two things you will probably have to worry about. Okay, because your drain and source series resistances will be due to metal lines. So let's say you're contacting down to the substrate, to the transistor drain and transistor source. You'll usually have metal lines, and all you have to do is make sure you have enough number of contacts to come up to the right metal. You have enough metal width for current density and resistance, and you're good to go. Okay. Now Rg, it so happens, directly relates to your transistor dimensions. Okay. So if you have transistor of a given width and length, so drain and source contact through metal directly to the diffusion. Problem with the gate is it contacts from the metal down to poly, which is relatively high resistivity, and then that is the gate. The poly itself is the gate. Okay, so let's look at a couple of cases. So let's look at a W over L of, take a quick example. Have you seen before? Do you know what multi-fingered layouts are? Do you know what number of fingers in a transistor is? Some of you might know. Do other people know? Okay. So let's say you have a transistor like this. Okay, 10 microns by 0.13 microns. Okay. So how would you? What would the transistor look like? The layout. So the layout is the top view of the transistor. Okay. And let's use red. Okay. This is what the layout of the transistor would look like. So this is the length of the transistor. Okay. And this would be the width of the transistor. Have all of you seen pictures like this? I'm sure you have seen pictures like this before, right? Okay. So of course, then what you're going to do is, I won't show it here, but you're going to put contacts on the drain, contacts in the source, and take it out as metal, right? Okay. So what is the gate resistance? So let's say this is the poly, this thin rectangle here. Okay. So what will happen is, your transistor is actually a distributed structure, because your gate signal is coming in from here and it's traveling all the way down here. Okay, so you're lumping it as a lumped resistance Rg, but this is the overall transistor, so you're going to have some poly resistance associated with it. How can you reduce this resistance? So what we'll assume is, we'll assume that R metal is much smaller than R poly. Okay, let's start off with that. What can you do to reduce the gate resistance? So one thing you can do, so here you are contacting it from one side. One thing you can do is, you can put a similar gate contact on this side. So let me remove this here. Something like this. Okay, so in a coarse way, okay, so remember that I told you this is actually a distributed resistance, but in a coarse way you can see that this will at least halve the resistance. Okay, so this is one way. Okay, in fact, if you pick up a standard RF process, they will have transistors which are, they're called RF transistors, so they'll already be modeled in this way. Okay, so if you look at the transistor layout, it will already have contacts on both sides. Okay, similarly, it will have many of these layout techniques which we are going to talk about here. Okay. Okay, what is the other thing you can do? Okay, what you can do is, you can fold the transistor vertically down. Okay, and this length still remains 0.13 microns. Okay, and then all you have to do is and you can do dual gate contacts also, and that's okay. Okay, so this is called a multi-fingered layout. So you can increase the number of fingers and trade off your gate resistance. Okay, in this case obviously your gate resistance is half in a coarse way. So you have Rg by 2, Rg by 2. So the actual resistance is Rg by 4, not Rg by 2. Okay, if your original transistor had resistance Rg, now you have half the poly length. So in a coarse way, you have half the poly length. So you have Rg by 2 in parallel with Rg by 2. So it's actually Rg by 4. Okay, but of course this is a very coarse approximation. I'll give you the general expression. You can take a look at it. You can use it. So the reason I'm giving you this is because in your design, let's say you have a 200 micron transistor. Okay, don't use a single finger which is 200 microns long. Okay, you will definitely have problems with that. Okay, in general, in an RF sense, don't try to use transistors longer than 5 microns, the width of each finger. Okay, so if you have a 200 micron transistor, try to have maybe 40 fingers at least. Okay, now the other thing to remember is, yes, yes, there is a problem. So the minimum size you are probably allowed to use, let's say in a 0.13 process will probably be like 0.25 by 0.13. Okay, that is actually a very suboptimal layout, because what will happen is, so when you actually increase the number of fingers, right? So effectively what you are doing is, this is actually two transistors in parallel. Okay, what you will do is, you will increase the effective amount of parasitics for each transistor when you go below a certain threshold for your width. Okay, remember we have not considered, for example, capacitive parasitics. Okay, those kind of things will start getting suboptimal after some point of time. Okay, so normally I wouldn't go below a micron, okay, of width. Okay, in your case it probably won't matter. It will matter more when you do the layout and run an extraction for your parasitics.
Simulation also, if you put finger, then the perimeter effect will be different than
Definitely. So it will get better. Okay.
Will it get better or worse?
The drain capacitance will get better. Okay. The source capacity, the drain capacitance will reduce. The source capacitance will increase. Okay. When you do multiple fingers. Okay. That is another effect. We'll probably consider it later. You know, I'm assuming that all your designs, you know, will be less sensitive to capacitive parasitics because you're tuning. We'll consider it probably at one class at the end. I'll have a layout class where I'll go over many of these effects. Okay, this I just wanted to give you so that you don't, you know, end up doing a design. What will happen is, you'll compute your noise figure and suddenly you'll see that a lot of noise is coming from your gate resistance of the transistor. Okay, and you won't know how to reduce it. So just try to keep these little things in mind. So don't have the finger width less than 1 micron, not larger than 5 microns. Okay. How about bulk? This probably won't affect you, but this is the other thing which is usually most important in an RF layout. Okay. So if you look at the layout, right? So let's go back to our layout. Okay. So you have the gate drain source. Where's the bulk? Right? The bulk is actually the background. So all of this area is the bulk. So normally what you'll have to do is, you'll have to put in what are called substrate taps or bulk contacts around the transistor. Okay. So effectively what you're doing is, so your bulk is actually, there will be a common connection to the bulk for the overall chip. Okay, but that will be very far away from your transistor. Okay, and that will be from the bottom side. Okay, which will be 500 microns depth, at a 500 micron depth. Okay. So what you'll have to do is you'll have to make sure this transistor has a good bulk contact. To do that, if you look at normal RF layouts, what you'll see is, so I'll just do this. So what you'll see is, you'll see something like this. Okay, you'll see it will look like this. Okay, this is actually a substrate ring. Okay, it's a ring around the transistor full of substrate contacts, because you want to make sure the RF transistors are especially sensitive to substrate effects. Okay, so you try to make sure it has a very good substrate, because the actual connection to the substrate may be very high, may be very far away. So what you'll try to do is, you'll try to connect it here and then connect it on metal to a good ground. But this won't affect you in the schematic. Okay, in the schematic you'll have to model this effect separately, because in the schematic you only get the 4 transistor model, right? You'll only get this bulk node, and you'll probably connect it to ideal ground in your case. Okay. Okay. So let's say you have an RB. So the noise from this is 4 kT RB delta F. So the noise on the transistor at the transistor output is 4 kT RB GMBS square delta F. Okay. So we will stop with that for LNAs. You have any questions on LNAs? We are going to move on to mixers. Any other questions for your project?
How can this last noise current expression?
So what is the voltage noise from the RB? It's 4 kT RB delta F, and that is at the bulk node.
So that converted to LNA.
This bulk node, and you actually have a GMBS here in parallel with GM, right?
So GMBS is considered after RD or before?
GMBS is considered?
After RD or?
No, before RD. I'm assuming that RD, the intrinsic resistance, right, is already included in the model of the transistor itself. These are all extrinsic sources. Okay? Okay, we'll move on to mixers then. Yes, yes.
So while modeling the inductor, we considered the substrate capacitance.
Yes.
Is like in parallel to RB, should we have a substrate capacitance?
Yes, definitely. I mean, you'll definitely have a substrate capacitance also, except that it doesn't produce noise. Okay?
That will add a pole and.
Sure, but it will be very, very far away, right? You're trying to minimize RB, right?
You don't have a that impact.
Yeah. And you're actually, once you give a ring, right, the resistance and the capacitance both will be very small, because you're giving a local contact for your bulk. Okay. What do we know about mixers? So they're used for frequency translation, right? That is a basic use. Okay. So you have two kinds of mixers. So in the transmitter, you're going to use it for what is called up conversion. Of the baseband signal to RF. And in the receiver, you are going to use it for what is called down conversion. Okay, of the RF signal to IF or to baseband. You can do both. Okay, and we have looked at this many times before. So a simple model of the mixer is just a multiplier. Okay, and if you assume this is and ARF cos omega RFT and ALO cos omega LOT, you know, we've calculated this many times before, right? Right, you can just multiply and choose the common terms. Okay, so you're just writing cos A cos B as cos of A plus B plus cos of A minus B by 2. Okay, so one of these is going to be the desired IF. Let's say if you have a down conversion mixer. Okay, so this would be your desired IF term, and this would be the term you throw away. Okay, so let's look at some metrics that you would use to characterize a mixer. So the first one is called conversion gain. Okay, so what is this? This is the amplitude of the desired IF output by the input RF amplitude. In this case, what is it? Okay, in this case it's ALO ARF by 2, which is the amplitude of the output, okay, over ARF, which is ALO by 2 in this case. Okay, because we are considering a very simple multiplier mixer. Depending on the mixer configuration, the conversion gain will change. You will find that there are cases when the conversion gain can be less than 1, and that's perfectly acceptable. Okay, it all depends on your noise figure. If you get enough gain upfront from your LNA, you can have a conversion gain less than 1 for your mixer, as long as you keep the noise also low. Okay, and you'll see, we'll come to that. We'll find that there are mixers called passive mixers, okay, where you don't have any gain, inherent gain, you actually have a loss. Okay, next one is noise figure. Okay, what is your noise figure defined as? Let's use remember we looked at definition SNR in over SNR out. So it's SNR at the RF port over SNR at the IF port. Okay, okay, so that is very easy. I mean, you can just do it the normal way, the way you would calculate your noise figure. But just keep in mind there are a couple of things you need to know, which are special to the case of mixers, okay, which you wouldn't have encountered in LNAs. There is one case for noise figure and there is one case for IIP3. Okay, for noise figure, just remember that you have to be very careful about your image frequency. Okay, remember we calculated how your image translates on top of your RF signal. Okay, and that's why you have what is called an image reject filter. Okay, so you have got rid of all the signals at the image frequencies. You remember that, right? Everybody remembers the image frequency. Okay, if it's omega LO, so omega LO minus omega IF is omega RF, omega LO plus omega IF would be omega image. Okay, so what happens is you have filtered out all the signal, okay, but you will still have broadband, the broadband noise floor would still be there, okay, and that will get translated on top of your signal. Okay, so you have to be very careful. So let's just draw it out, it's a lot easier to see it. Oops, sorry. Let me exaggerate it a little bit so that we can see it much better. Okay, let's assume this is your noise floor. Okay, so you have a noise already coming in, some SNR coming in. Okay, but let me. So let me draw it a little bit better. So let's use this guy. So this is your image frequency. Okay. So if you look at the output, okay, at IF you are going to have your RF signal, and of course the noise from the RF, but you are also going to have noise from your image frequency band. Okay, and this would be the case in most mixers. Okay, because you will be interested in only in one sideband, the other sideband. So you can actually define, there are actually two definitions of noise figure. One is called the double sideband noise figure, the other is called the single sideband noise figure. Okay, so this would be what is called the single sideband noise figure. Okay, when you compute the double sideband noise figure, okay, it depends on when you, okay, so let me draw it with a slightly different color. We use this guy. When you compute the double sideband noise figure, what you would do is you would have useful RF signal at both the RF frequency and the image frequency. Okay. So what does that mean? Yeah. Okay, your single sideband noise figure is going to be larger by your double sideband noise figure by 3 dB. Is that clear to everyone? Okay, so if you look at a paper which quotes a particular noise figure, read it very carefully to find out whether they are quoting the SSB noise figure or the DSB noise figure. Okay, there are some people who quote SSB, some people who quote DSB. So it may look artificially better if they just quote the DSB. So the thing is, there are some cases, okay, where, okay, so in most cases only SSB noise figure is right, okay, but it depends on how they characterize the noise figure. There are a lot of people who put useful RF signal on both sides and then measure the noise figure and they'll quote DSB, okay. There are some cases where you could have useful RF signal on both sides, very rare cases, but you could have it, okay. In those cases DSB noise figure makes sense. Okay, but a majority of the cases SSB noise figure is what is useful. Okay. You'll have to see. There are people who quote DSB noise figures. Okay. In DSB? No. The whole point is, okay, in both cases SSB or DSB measurement, you have the noise floor from the image and RF frequencies come down to IF, to the same frequency band. Okay, the noise is additive in both cases. The question is whether the signal is additive or not. Okay, in the case of SSB, you have signal only on one side. That's the first case we discussed. In the DSB measurement, you would have useful RF signal on both sides. Okay, that's why it's called DSB, because you have a double sideband RF signal. Is that clear? Sure, yes, definitely.
So it is equivalent of considering only one noise level. And if I have only RF and its own noise flow, whatever
yes.
I will get, that is exactly the same as considering two sideband.
Exactly, that is right. That will be exactly the same as considering two, right? If you don't have a noise, but you can't see in a measurement, you can't constrain the noise at the image frequency. Whatever you do, right, as far as filtering goes, the noise floor will still be there. There will still be some, broadband noise coming in. Okay, you can get rid of the signal but not the noise, because the noise floor is typically very much lower. Okay, One more thing to note, okay, unique for a mixer. Let's say your mixer is completely noiseless. What is your single sideband noise figure? Let's say your mixer is absolutely noiseless, ideal. What is your single sideband noise figure? And what is your double sideband noise figure?
Still the whatever information are coming through that noise.
Which is the case for a?
For in case of single sideband, it will be 3 dB worse because
3 dB worse than double sideband, but that is true for any measurement, right? So I am asking specifically in the case where the mixer is ideal. Let's say it's noiseless.
it will be 3 dB worse from the input in case of single sideband because still
Okay.
the noise from the image figures will be
Correct. And in the case of DSB, what is the noise figure?
same as,
Will be same as what?
input,
Yeah, and so no, I understand the SNR is the same. What does it mean for the noise figure? 0. I mean, if a system is noiseless, noise figure is 0. So in the case of DSB noise figure, it is 0 because SNR at the input will be the same as SNR at the output. Okay, but note that even if you have a noiseless mixer, your single sideband noise figure will still be 3 dB. Okay, that's very important. Just remember that. Okay, because your useful signal is coming only from one side, but your noise floor is coming from both sides. So okay, so you have an input noise floor. Assume that your mixer doesn't add any noise. Your image noise will still fold over, which is your input noise. So your input noise effectively gets worse by 3 dB, but your signal stays the same. Right?
Basically, in that ratio,
Yes.
the ratio will be a 1.
In the case of a double sideband. In the case of single sideband,
It will be 3 dB more.
3 dB more. Right? Okay. So assume your mixer is noiseless. Okay. So in fact, this figure we have not even shown where the mixer noise is, where the noise coming from other circuits are. But assume that input broadband noise is like this. Okay. And assume that you are considering the double sideband case. So you have an RF signal here, you have an RF signal here, and the mixer is completely noiseless. Okay. What is the SNR at the input? You have some SNR at the input. What is the SNR at the output if the mixer is completely noiseless? Same as the SNR at the input. Okay. Why? You are going to get signal from RF to IF here, signal from RF to IF here. Same thing for the noise. So SNR at the output is same as SNR at the input. So noise figure is 0 dB. Okay. Now consider the single sideband case. You have the signal only on one side. But you have noise on both sides. Image band noise will still come through. That is the input noise. No noise from the mixer. Okay. So the thing to remember is, okay, at the input, your noise looks like this. Okay. What happens is, just like your signal effectively folds over around your LO. Remember that? Okay. So this one goes to IF. This one goes to IF also. Right? Just like that, the noise above LO will also come down around this. Okay. What that means is, and it's broadband white noise, totally uncorrelated between frequencies. So it will become 3 dB worse. So the noise floor gets 3 dB worse, whereas the signal just comes through directly. So automatically your SNR at the output is going to be worse because your noise floor is no longer the same as at the input. Is that clear to everyone? So you will see these kind of, so whenever you have either nonlinear or time variant circuits and the mixer is nonlinear and time variant, you will see issues with what is called noise folding. Okay, you will see noise coming from other frequencies. So in an LNA, when we looked at the LNA, it was a linear circuit, but it was time invariant. It was somewhat slightly nonlinear. But it was time invariant. Okay, so if you have an input noise and an input signal spectrum, at the output you will have almost the same input and noise spectrum. Whereas in the case of mixers, VCOs, any kind of switching circuit which is nonlinear, you will see issues with noise folding. Okay, you will see noise coming from higher frequencies, lower frequencies to your desired frequency band. Okay, then the next one, okay, so typical noise figure is for an active mixer would be 10 to 15 dB, would be very common. Okay. And that itself tells you why you need your LNA, because obviously 10 to 15 dB is not going to cut it for any receiver. You want it to be like 2 to 3 dB for the overall receiver. Okay, let's look at linearity. Again, as before, you would characterize it as IIP3, or sometimes occasionally people will also call the output IP3, okay, OIP3. But usually IIP3 is the standard metric. Okay, and why do you need this? Because we all know this, right? So you have a desired RF here. So you could have two signals coming in, and so a typical mixer, you could model it as some kind of nonlinearity. So we'll look at signals in all three cases. So at 1, if you have the RF signal and the two interferers coming in, okay, so let's draw it a little bit more systematically. This is at 1. You would have the third order intermod product coming in at 2, okay, and of course at 3 the whole thing gets down converted. Okay, so you definitely have problems with linearity, as in the case with an LNA. Okay, but one thing to note is that uniquely in the case of a mixer, okay, so in the case of an LNA, so let's say you only have a single input, single interferer, okay, could it cause a problem? Thing is, if you have a single interferer, first harmonic, second harmonic and cubic, let's say you have considered a third harmonic for your LNA. Okay, so your single interferer would have a first, second, third harmonics, which would fall, second and third harmonics would be far away from your desired signal. The first harmonic would be the same distance away as at the input, so nothing special about it. In the case of a mixer, on the other hand, you could have a problem if you have a cubic nonlinearity and if you have even a single interferer at the input. I'll give you an example. Okay, so consider the case of AM radio. Okay, your IF frequency is 455 kilohertz. And assume that your channel that you are interested in is 910 kilohertz. What is your FLO? Is 1365. You're again assuming high side injection. Okay, so assume you don't even have an interferer, you only have your RF signal at your input. Okay, so your RF cubic term, okay, would generate at 2 omega RF minus omega LO term. That is your IM3, the cubic. Okay, what is this? In this case, it happens to be the same as the IF frequency. Okay, the main reason this comes about is because your output frequency band is not the same as the input frequency band. Okay, so your earlier in the case of the LNA, any cubic terms would fall far away from your desired RF signal because the output frequency is the same as the input frequency. In this case, your output frequency could be much lower or much higher. So you could have problems even with a single input. Okay. The fourth metric is isolation. Okay. So let's say you have an LNA. So you have your IF amplifier. Okay. Now consider what happens if some of your signal, LO signal, leaks through to your IF port. Okay. Remember that compared to your RF signal, your LO signal is usually much higher. Okay. Not remember that. I don't know if I mentioned it earlier, but your LO signal is usually much larger than your RF signal. Okay. You remember your RF signal is in microvolts. After the LNA, it will probably be in hundreds of microvolts, maybe millivolts. Okay. Your LO signal is usually in hundreds of millivolts, or maybe greater than a volt. Okay. So there is every chance that the LO signal coming in is much larger than your RF signal. Okay. What happens? You could saturate your IF amplifier. Okay, that is your LO to IF. It's called your LO to IF feed through. Okay. How about the second case? So let's take the same thing. Okay. So what happens if you have LO to RF feed through? So your LO to RF, LO to the output input of the mixer, okay, could happen inside the mixer itself. Okay. LO to the input of the LNA would happen through other means, electromagnetically or through the substrate. Okay, so through parasitic paths. What will happen? Once it gets here, you would see what is called re-radiation. Okay. So the same signal which comes in, remember it's an antenna, so it radiates out into space. This is called re-radiation. Okay. One more problem is in what are called homodyne receivers or direct conversion receivers. Okay. The major characteristic of these receivers is that the IF frequency is 0. Okay. So you don't go from, in the receiver, you don't go from RF to IF and then to baseband. You would go directly from RF to baseband. So your IF frequency is 0, which means your LO frequency is the same as your RF frequency. Okay. Then what happens? Okay. So what you want is omega LO minus omega RF at the output. So let's say you have something leaking through here. What happens? If you look at the output, ideally you want your RF signal, okay, but because your LO feeds through here, first of all you're going to get a huge DC component, okay, which depends only on your LO amplitude, nothing else. It doesn't depend on the RF at all. So if your signal has any information at DC, that's lost. Second thing, if there's a delay, okay, remember these are very high frequencies we are talking about. If there is a phase delay or some other kind of delay between the input and the output, that could cause a slowly varying signal at the output. So you could have some information loss at low frequencies also. Okay, so this is a major problem for direct conversion receivers.
So
Yes, so you can, okay, so you can if, so this kind of feed through could be a characteristic of your mixer itself. Okay, I'll give you a simple example. If you have a transconductor, you could have a gate to drain capacitance which could cause feed through. We'll see it. Actually, next class we're going to look at it. We'll see that it could be a characteristic of the parasitic path through the mixer itself. Okay? Okay, so let's stop here. Continue next class. We'll continue with other kinds of mixers. And in the meantime, if you have any